Hello everybody. Let's start today's lecture. Last time we started talking about morphology, and in fact, before we studying morphology, we reminded us the concepts of finite state automata, deterministic automata, and non-deterministic automata, etc. And then we started studying English morphology. Then I gave you a paper for you to read about Turkish morphology. The kind of morphology that we are following with this technique is a two-level morphology. Two-level morphology. Okay, why two-level morphology? I mean, can it be like just a single-level morphology? It could, and in fact, the finite state transducer that we are going to build are going to be just one level, but two-level is good for us, for human designers. It will be clearer for us what is working, how, and why. Okay, so let's try to remember what we said last time. Okay, we talked about the English morphology and its relation to finite state transducers. And with the morphology, what we mean was study of the words, right? That's what we said is the study of the ways words are built up from smaller meaningful units called morphemes. Okay, morphemes are either stems or affixes, kök ve ek in Turkish, right? We usually have a stem and we add affixes to the beginning or ending of the words. And in Turkish, usually it is the end of the words for Turkish words. Let me try to... Okay, my captions. Good. That's what we said last time, and these are some of the things that I have introduced. We said that in English, like Turkish, there are two types of morphological operations on words, like the inflectional morphology, which is çekim ekleri in Turkish, and derivational, which is türetme in Turkish. With the inflectional morphology, for Turkish it is both difficult. There are lots of rules, there are lots of exceptions, there are lots of ways you can do both inflectional and derivational. In English, inflectional is a little bit easier, quite easy, especially for the nouns. For the verbs, it's a little bit more complicated, but derivational morphology is complicated. But most of the time, inflectional morphology is what we need, because, I mean, when we do the inflectional morphology, the root of the word stays the same. Okay, the root of the word is the same function grammatically or semantically. So we need the root of the word really bad, and for Turkish it is not that easy to get that one. Okay, and we said that for now, for us, the words are just two groups: nouns and verbs, isimler ve fiiller. Nouns and verbs. Of course, there are many more classes of the words, but we will look at them later in chapter 5 when we do the part of speech tagging. Okay, again, inflectional morphology is the first one that we're gonna look at. I think we looked at it for English. For nouns, especially for the inflectional morphology, it is simple, very simple. For the nouns, it only could be a singular noun and plural noun. And for the verbs, it is like the verb itself and the ing, postfix, and the ed, sometimes the past tense, past perfect tense, etc. That kind of things makes it more complicated for the verbs. Okay. And for English, actually, the problem comes with the morphology is the irregular nouns or irregular verbs. Okay, so for the nouns, for example, we don't say mouses, we say mice. Okay, we don't say oxes, we say oxen. So there, their non-singular versions are not derived with a rule. There are exceptions, so there are many of them for the nouns. For the verbs, okay, the past tense versions are not regular for some words, for some verbs, and we need to be careful about them. And these makes it more complicated for the English words. Okay, regulars are okay. For a verb, all the inflectional morphology can do is walk, walked, walking, walked, walked. Okay, but in Turkish it is yürü, yürüdüm, yürüyorum, yürüyormuşçasına, yürüyorlarmış, yürüdüler, yürüler, yürümüşler, yürümüşler, yürürlermiş. It is very complicated. This is so many versions of the same verb inflected differently. Okay, of course irregulars are there too. Okay, and in Turkish there are irregular morphology cases too. Okay, so but we as humans we don't realize that, and we just use them. Okay, can I have a minute? Let me grab a cup of tea. Sorry, I'm coming back. You grab a cup of tea too. Okay, so it's my tea. Again, for English, inflectional morphology is I mean, if you consider it as complicated compared to Turkish, it is. What? Somebody did something. Come on. Somebody stopped my recording and they started their own. That messes up everything. Don't do that, guys. So what am I gonna do now? Stop this recording. People, please don't play with my recording button, okay? If you stop recording or again start recording yourself, it messes up everything. It shouldn't, but the stupid Microsoft interface. Okay, I hope this fixes it. Anyway, I am recording it locally. Okay, so derivational morphology is more complicated. We talked about this because there are many ways that you can derive new words, either nouns or verbs from other words, and this is as complicated as Turkish maybe. Okay, and we are not. I'm not going to look at them more carefully, and sometimes I mean, not all rules apply for all the words. For example, there is clue. Okay, I mean clue is a noun, right? Clue and clueable. I mean, can you do it with all the nouns? No, clueable. There is no such word as clueable. Okay. So it doesn't apply for all the words. We know that. So, but we can, whether it is applicable or not, we could use finite state automata to make these kind of decisions. Either, remember, finite state automata could be used for recognition, for the generation too. If I have a finite state automata like this, okay, for any regular noun, I accept it. For any regular noun plus the minus s plus the s affix, I recognize that too, okay. For irregular plural nouns or for irregular singular nouns, I always go to the accept state. So for simple, very, very simple rule, okay, that means that I need to get a list of regular nouns and irregular nouns. For the regulars, just this minus s is okay. Okay. This minus s is okay. That means like if cat is a regular noun, cat is a regular noun. Okay. Cat is a regular noun. If I use that regular noun, I accept it. But if my input is cats, then that's okay too. I accept it like at here. Okay. So this is a simple case, very, very simple case. Okay. So start with the simple rules like this. Then you add in your words like this. Okay. Cat, cats, goose and geese, these are all irregulars. Actually, there is something wrong with this picture. Can you tell me what is wrong with this picture? Can anybody tell me what is wrong with this picture?
Foxes.
Yeah, the foxes doesn't, we don't write foxes like that, okay? We write foxes like this. So this doesn't handle everything, so we need to do something. And do you guys remember this one? What do you call this? We call this, oh, let me turn on my chat window.
Epsilon.
So what does it mean? Epsilon. Everybody knows that it's a Greek letter, or I don't know what kind of letter it is. So it means what?
Anything other than S.
Anything what?
Anything other than S. S affix.
Well, actually, yeah. Well, it is not anything other than S. No, it is not.
It means maybe sometimes get S, sometimes with ES or something else. There is no rule.
It means match nothing. Okay? It means match nothing. Okay? Sometimes with cat, if there is no S at the end, I will accept it because I can do this transition without any input. So this is empty transition. Okay? Null transition, empty transition. I don't need to read the input to take this transition. So this makes this finite state automata a non-deterministic finite state automata. Okay, if somebody tells me that I have cats, okay, so I come here, I see C here, A, then T there, and I can choose this one because I don't need to see an input, and I come to this accept state, but I have one S remaining. That's not a good state then. Then I need to go back and follow the other path, okay, in order to accept this cat string, okay. So that's a empty transition. That what makes this finite state automata. Non-deterministic. How would you eliminate this empty transition to make it more deterministic? So all you do is just eliminate this one, right? Eliminate this one and make this a final state, right? So this could be a solution too, but they didn't prefer it that way. what they did was there is only one final state and that's it. Okay. Okay, yeah, what Doğancan is saying is right. So there is another finite state automata. This time it is okay. This is for the inflectional morphology. What was the rule? Start with simple stuff and add all the words and irregulars and everything. And this is for derivational rules. If you, what is noun I? What is noun K or verb K or noun L? What is noun I? Can somebody tell me what noun I is? Noun I. What is noun I? Okay, time to go back to our list and let's pick somebody from the middle. No, from the end. Let's pick from the. Okay, Yaşar Kemal Yavuz. Yaşar Kemal, tell me what is noun I? What is the difference between noun I and noun L? Oh no, Yaşar Kemal is not here. Sorry. Okay, then in that case, Yiğit Yağız çaktı. Yiğit Yağız. Okay. What is the difference between noun I and noun L? Is Yiğit there? I don't know is that a good answer. You need to tell me with your voice. Use your microphone. I don't know means I don't care, okay? If you don't care, then don't attend this class. I am not expecting to know something that I just showed you. I just want your opinion on it, okay? Just look at it and try to tell me something. Ityaz, we are waiting for you. Tell us something.
I don't know what to say.
You say something other than I don't know what to say. Are you looking at my slide? Are you listening?
Yes, I do. There is noun I, there is a noun L at the bottom and noun I at the
Okay,
top.
so if you follow noun I, what do you see?
It goes to Q1, state 1.
Doing
And
what?
noun-
With what? With what? It goes to from Q1 to Q2 doing what?
No, it goes from 0 to 1 when it's I, isn't
Yeah,
it?
and after that, what does it do? It goes to from Q1 to Q2 using what?
Eyes.
I. So just come up with an example, a noun that can take an eyes.
Plagiarize.
What?
No.
Say it again.
Plagiarize.
It has to be a noun. For example, maybe we can go back and we can look at these examples. Yeah. See this computer?
Yeah, that also works.
This,
Computerize.
Computer. If I say computer, then computerize makes a noun a verb. Then computerization makes it another. It was a noun. Now it's a verb. Computerize. Computerization is another noun. Okay. So noun I is kind of a noun class that can take this eyes suffix, right? To make it verb. So for computer
Yes.
it works, but for book it doesn't work, right? Book eyes, we don't say book eyes, right? So book is not in class I. How about noun L? Noun class L, so it is ative. Yeah, okay, so can we say bucative? Bucative? No, I never heard such a thing, bucative. Oh, sorry. This is verb. So I am looking at noun L. It is full. Okay. Can we say book full? No, but we can say tell me a noun that ends with a full.
Maybe helpful.
Yes, help. Help is a noun. If you think it as a, I mean, help could be a verb or noun, but when you say it, helpful. Yeah. Okay. In fact, we have adjective in here too. So what I am saying here is that these kind of rules, they expect you to assign class numbers to your nouns and adjectives and verbs, and for that class of nouns, this rule is applicable. This rule is applicable. This rule is applicable. Okay. So if somebody says book eyes instead of computer eyes, okay, this finite state automata will not accept it because book is not in the ith category. Okay. Okay, somebody is weaponized. Doğancan, you don't have a microphone? Factorize. Yeah, we have very good respect. Respect is for respectful. Yeah, okay, good. Mindful. Okay, good. Those are very good examples. Okay. And I mean, there's similar stuff. In Turkish too, by adding some sonek to the root of the word in Turkish, we can have different verbs, different nouns, but those kind of rules are not applicable all the time. Good. So let's look at this. I mean, it is nice that we can have this kind of finite state automata to recognize words, either nouns or verbs or adjectives, doesn't matter. It is nice, but it would be even nicer if this kind of recognition would produce us some kind of a parsing. For example, when I say cats, okay, I recognize it. I like to have this final result. I recognize it, and I recognize it by assigning noun to cat root and adding a plural suffix at the end. Okay. This is called parsing. Okay. If we find a string in the language, we might like to assign a structure to it. Okay. So this is called parsing. We morphologically parsed this word into this one. Okay. Good. So we are gonna do it. Actually, this is kind of does that. From noun I to verb, then noun, and we are doing that. So for all the words, we are going to assign these kind of strings to the surface forms. This is going to be the surface form. At the surface, we see this, but underneath the surface of the sentences, with the morphological analysis, we will have these kind of morphological parses, and that's what we are gonna do with the rest of this chapter. Okay, so well, I mean, for now, what we did was just get an input and try to reach a final state. Now we are gonna do that too, but at the same time, we like to produce another string. Okay, so that's called finite state transducer. Finite state automata. Okay, it says yes or no. It says I recognize it or did not recognize it. But finite state transducer, it also says yes or no, but as a side product, it produces this kind of string that shows us the parsing. Okay, that's a new mechanism. So at the surface, I have this with the lexical analysis, morphological analysis. Okay, this is lexical form, surface form. Okay, lexical form is the result of the morphological analysis. With the lexical form, I have cat as the root, is a noun, and I added a PL. Okay, that's our ultimate goal is with the morphological analysis. Okay, but with the morphological analysis, parsing, okay, we can do many things. It could be a standalone natural language processing application if you do the morphological analysis parsing, or it could be a first phase of a more complicated natural language processing application. Okay, so the book says that, for example, for spelling correction, we could do this morphological analysis, and if it goes through, then I know that this is a correctly spelled word. If it is not, then it is not a correctly spelled word. Okay, or we could be a part or information retrieval. Can somebody tell me how we can use the morphological analysis results with the information retrieval?
We can look at the stem of the lexical analyzed sequence.
Exactly, yeah. I mean, usually with the information retrieval, your questions, you don't expect them to be grammatically correct. Okay, all you expect is just a set of words. Okay, and you like to have the stems of the word so that you can make a search on it on your database, right? For information retrieval, we could use that. Or again, we can use this morphological analysis as the first step of a further analysis such as machine translation. Okay, so it's an important natural language processing phase. Okay, let's go back to finite state transducers. This is a finite state transducer. Now we have 1, 2, 3, 4, 5, 6 states. Okay, transition from one state to another state. Now we have this notation. See, CC means that read C from your input and write C to your output. Read A and write A. Read T and write T. Read plus N and output nothing, epsilon. Okay, read plus PL, it's the label for the plural. Okay, and write S. Okay, this is a finite state transducer that transduces from lexical form to surface form. Okay, if you give this lexical form, it will recognize it first. Okay, and it will also produce the surface form. Okay, it will also produce the surface form. Of course, this is just for one. This is just for one case. Okay, case of cat. Okay, for typical uses, again, finite state transducer, we are going to read from one tape and we are going to write to another tape, and our second tape will have our results. And of course, ambiguity will be there as always with any NLP application. Ambiguity will be there. That means that you read from one tape. When you write to another tape, you might have more than one parse. Okay, so your finite state transducer might recognize the same input in many different ways. Okay, in many different ways. And most of the time, for example, for spelling applications, for example, when you say kitabı in Turkish, okay, as long as you write kitabı as a spelling, it is okay. Okay, the kitabı is okay because it is spelled correctly. But kitabı has many meanings. It is either onun kitabı, right? Onun kitabı, iyilik eki, or bana kitabı ver. In that case, the accusative form of the word, right? Or there could be, are there any morphological meanings of kitabı? Çocuğun kitabı, kitabı ver. Can you think of any other morphological analysis of this kitabı? I don't. Maybe there are. I don't. So it doesn't matter for spelling application which path you take, it is spelled right, okay, for this application. But for some applications, which way you parse it is very important. Because when you say onun kitabı, it translates as his book. When you say kitabı ver, then in that case, give me the book, okay? Then you have to put a the at the beginning of book, okay? And there are, like in Turkish, in English too, there are many ways a word can be parsed in our finite state transducer. Unionizable, it could be either unionizable, unionizable. Well, it may not be meaningful semantically, okay, but it is a morphologically valid parse. Okay, so how do we deal with this ambiguity again? Either for spelling application, doesn't matter how you parse it, it is okay. For the spelling application, it is okay. As long as we have at least one parse, we are fine. For the other applications, okay, we might choose different ways of choosing it, okay. Sometimes they say that I will take the first one, okay, return them all or take the first one. Sometimes they say that, okay, I found many, but this one is more likely. So this is a statistical approach. This is like statistical. Okay, this one says that I'm going to return you all of them or just the first one. Okay, so let's go back to our finite state transducer and let's try to deal with these kind of cases, geese, mice, and oxen. And also remember this one, cat and dogs are okay. Geese and mice and oxen are irregular words, okay? So their singular version and plural versions they don't follow the rules. But fox and foxes, they are not irregular, okay? Still, we don't say F-O-X-S, we spell it this way. So the rule is a little bit different. So let's try to see how we can do that kind of processing with the finite state transducers. The thing is this, there are many rules in English, and Turkish is the same, that can be used at the same time. Some of the rules are applicable for some of the words, some of them are not applicable. And this makes it more complicated. I mean, this makes it, when you give the surface form, there is a finite state transducer, and you produce the lexical form, morphologically analyzed form, right? That's what I expect, and I like this to be a single large finite state transducer. But for us as human beings, it is not easy to write these kind of finite state transducers. It is too complicated. So what we are going to do is, we are going to take this surface form, okay? We will have many finite state transducers. Some of them are applicable, some of them are not applicable, okay? And we will produce a intermediate form. Then after that intermediate form, it is easier to get with a finite state transducer to lexical form. or maybe I should do it this way. Okay, so these will be simple rules, and each one is either applicable or not applicable. So we are gonna do this idea, multi-tape machine. Okay, to deal with these kind of complications. Okay, we will add more tapes, and we will take one input and we will produce an output, and output will be produced by some other finite state transducer. Okay, so to handle irregular spelling changes, we will add intermediate tapes. It's like going to be this. This is the surface form. This is the form that we humans read. This is the intermediate form. Okay, this intermediate form does this dropping E or added E kind of stuff. And after that, I can do this lexical analysis. So one transducer will bring me from this to that, and from this to that. Note that this ES thing, okay, does not apply only to the nouns. For example, box. Okay, if somebody say boxes, it is either noun box plus plural, or it is box as a verb plus third person singular. Okay, he boxes the stuff, something like that. For intermediate form will be the same, but for lexical form there could be two parses. Okay, so intermediate form doesn't care about this noun stuff. Intermediate form only cares that I have seen E rule, added E rule, or dropped E rule, and I will handle it. And we are gonna see one example of finite state transducer that can handle this dropping E rule. Okay, E drop or added E rule. Good. Any questions? Okay. Here is the example. This is lexical to intermediate level. Lexical to intermediate level. Okay. If you have, or just the opposite, doesn't matter, because it is easy to change it. By the way, this sign is used for in the intermediate form, is used for marking the end of the word. Okay, this sign, and it is produced by this finite state transducer. Okay, so lexical to intermediate, it works this way: fox plus n plus plural. You will say here, when I see plus n, I will output nothing. Okay, and when I see PL, I will add this caret S and end of word. Okay, when I see singular, I will add just this. Well, okay, this part is kind of pretty straightforward from here to there or there to there. Okay, it is not that easy. It is not that difficult. Going between these two is not that difficult, because all you need to do is that if fox is a noun, then I will do that. If it's a verb, then I will do it the other way. Going from here to here, it is a little bit more tricky because I need to handle this E stuff. Okay, and this is, okay, add an E rule, finite state transducer, intermediate to surface, from intermediate to surface. For example, it will take this foxes, like fox caret S sharp to fox caret X, fox ES, and end of word. Okay, so let's try to see how it works. Let's try to take this one and try to produce this one. Okay, so this one says that Q0 get everything. Okay, if you see a caret sign, produce nothing, and for everything other, then you just take them and produce them. Okay, But of course, there are some exceptions. I have to be very careful about Z, S, and X. Because if there is a X at the end of the word, I will have to be careful. For example, box. It's going to be boxes, right? If there is an S at the end of the word, just give me a word that ends with an S. A noun. Tell me a noun that ends with an S. Okay, bus is good. And I have to be careful about, because the plural form of bus is not bus SS, it's buses, right? So I have to be careful, and I have to be careful with the Z too, because how about a word with a ending with Z? So this rule applies only to the words that ends with Z and S and X. Anybody with a word that ends with an Z? Nobody?
Fez.
Jazz? Somebody said something, but I didn't get it.
Fez.
Fez? What is fez?
It's Fez in Turkish. In English, it's Fez.
Fest in Turkey? Ah, okay. Nida, you say jazz, okay. Well, there is no plural form of jazz, right? Hertz, yeah, Hertzes. There is no plural form of Hertz either. Okay, Fezes, I think, is the. It looks like we are having difficulty finding common words with the Z. Anyway, for X and S and Z, I have to do this. It says that do this all the time. Okay. The only difference is when you see a caret sign, produce nothing, right? Produce nothing intermediate to surface. But when you see Z and S and X, then you need to go to Q1. Okay, so let's look at this Fox and S. Okay, so I take F. Can we do it like with the input F? I am at Q0, right? With the input F, I am back to Q0. When I get O, I am at Q0 again. When I'm at X, X will take me Q1. Okay, it will take me at Q1. Now I have a caret, this one. So where would I go with a caret here? It looks like with a sharp I will go back to beginning. Okay. With a caret I would go to Q2. So I would go to Q2. Okay. And I did not produce anything. Oh, by the way, here let me try to. Okay, F produced F, O, X. With the caret, I did not produce anything. See, with the caret, I did not produce anything. So Q2 means what? Q2 means I am at a position where I got the stem of the word, and I get rid of this caret thing, and I am at the end. If I am seeing an S here, okay, if I am seeing an S in here, I can go to Q5 or without seeing anything, I can produce an E. Since this is a finite state transducer and non-deterministic finite state transducer, and my purpose is to end up in a except state, I think I will take this path, right? So without seeing anything, epsilon, I will go to Q3 and I will produce an E. Then with seeing S, I will go to Q4 and I will produce an S. Okay, and then when I see the sharp sign, I go to Q0. Okay, when I go to sharp sign, when I see a sharp sign, I will go to Q0 and I will produce a sharp sign. So that's how it works. So this part of the finite state automata deals with this part of the words, okay? So this is intermediate to surface, but if I just change the inputs and outputs just the opposite way, it can deal with the other stuff. Question: what is the function of Q5? What is the function of Q5? It looks like Q1, Q2, I used Q0, Q1, Q2, Q3, Q4. So why do I have a Q5? Can anybody tell me?
I was gonna ask that, but I'm gonna guess now. Can it be for example, a word like boss?
Boss, yeah. Like, because when you say boss, when you make it plural, you need to make it bosses. But this S here, the first S, will take you from Q0 to Q1, okay? Q0 to Q1. And in that case, I don't wanna be fooled by this first S. Well, in that case, Q1 can handle it, right? Q1 can handle it, right? Yeah, because in that case, Q1 is going to handle it. Because if I have another S, I have a state at Q1, and like it's going to be S like that. So this part is for that kind of stuff. But here, if I have more than one, no. Okay, if there is an S, I would go to there, because I have this one, caret. It looks like this is a more part of a more complicated finite state transducer, and I use this caret sign for other to the division between the root of the word and the affixes, and for a different reason other than this singular plural stuff. If I am at there, then I need to handle it. So I couldn't think of a good word that will take me to Q5. Okay, but it looks like if you see an S, you just go there, and if you see a caret, you come back. Or if you see this, yeah, because the only way to move from Q1 to Q2 is the caret, and caret is not used for only this rule, then there are many other rules. Okay, so it looks like this thing is complicated. Even such a simple rule like adding an E, this is complicated. That's why the picture that I showed you, remember the picture that I showed you, there are many finite state transducers from surface to intermediate or intermediate to surface, okay? For example, this one is for adding E rule, okay? And This one is maybe for, remember when you say fly, it doesn't become, this one doesn't becomes, this one doesn't become flies, right? Instead it becomes flies. So I need another finite state transducer to handle this kind of adding s stuff, right? Because there is a conversion between y and I. So this one is for E, this one is for Y, and there are many other rules for English and similar stuff for Turkish. For Turkish, we don't say kitapı, we say kitabı, right? So there is a the softening of the final consonant there, and I need a rule finite state transducer for that, right? So there will be many of them, and each one is either applicable or not applicable, and these will work between the surface form of the word and the intermediate form of the word. Okay, so this is one example from faxes to lexical form. Okay, so this one, remember the first transducer that I showed you, and this one is from the second transducer. It went from 0, 0, 0, 1, 2, 3, 4, 0. And I think I did the same thing. 0, 0, 0, 3, okay. 1, 2, 3, 4, 0. Yeah. I started from the 0, then I did it that way. So 0, 0, 0, this part. 0, 0, 0, 1, 2, 3, 4, 0. Okay, 0, 0, 0, 1, 2, 3, 4, 0. Notice this one, there is an empty transition, so this one corresponds to the outputting of these two. Okay, and I have already showed you how this one works. Good. Any questions so far? Okay, Selman Yasin has a question. If finite state method FSM, what is this? Okay, wouldn't convert the wrong input like passes. Yes, that's true. Well, finite state transducers, I think by FSM you mean finite state transducers. If finite state transducer is a finite state automata, right? Its first task is either accept or reject. But rejecting is okay. Yes, I rejected it. This cannot happen. Rejecting is okay, but if you accept it, I like to know how it is accepted. I like to have this lexical string. Okay, I like to have this lexical string. That would be the output. But before producing that output, I need a yes or no answer. If the answer is no, there is no such a string. Okay, so finite state machine is a general term. Finite state transducer is what we are using here. Okay, good. The nice thing is, I mean, this one will reject. This one will reject flies, right? Because this is not applicable. This one will accept faxes, etc. So this one doesn't have to accept everything. But if this one rejects some other finite state transducer machine, will accept that fly thing. So the key feature is it doesn't have to recognize everything. If it is not applicable, it will not apply. Okay, so we have now one finite state transducer that has explicit information about one of the rules. Okay, and we have many of them, and these are the orthographic rules. Okay, this is adding an E rule, and this is dropping the Y rule. This is doing something, this is doing something. Each one is applicable. Okay, there are many of them. There are n of them. Their task is to give me this intermediate form, and then I have this main finite state transducer that works from this intermediate form to the lexical form. Of course, remember last time what did we say? If I have a finite state automata, transducer 1, and finite state transducer 2, right? I can make another finite state transducer by adding these empty transitions. Now I have a new finite state transducer. So at the bottom here, that's what I am going to do. I will put them together and I will make a single finite state transducer. I will make a single finite state transducer, and I have another single finite state transducer. So it will make two big finite state transducers. And in fact, using the composition rules, I can make this whole thing a single finite state transducer. So I will have one large finite state transducer, and as a human being, I won't understand what's going on inside it, exactly how it works, because these will be automatically produced by computer. All I care is that I have these orthographic rules and my lexicon finite state transducer. Okay, so I think it looks like I'm out of time for the first part of the lecture. Let's take 10 minutes of break. After the break, I will take your questions if you have any. If you don't have any questions, I will try to talk about this composition stuff. Then after that, we will look at our Turkish morphology paper and try to understand how they did it. Okay, 10 minutes of break. Let's be here at 1439. Enes getirmişti bunu ya.
Enes kim? Bu yabancı olan Enes.
Yok yok. Bizim şeydeki. KP'deki. Sabah seni bekliyor diyordu şey. Zaten seni bekliyor diyordu. Sabah ben gelemedim sabah. Bana da kadar sen değil mi?
Bu kaç oldu saat falan filan bana dedi. Nasıl geçti şey? Gördün mü onu? Nasıl gördün? Zaman mı? O kadar geçeceksin değil mi?
Sonra yani onun manasıyla şu zamanlar geçiyor. Yani bir metnin üzerinde ağaç çıkıyor. Bir metnin üzerinde değil. Sadece bunun üstüne de var.
Yemeyecek ama artık. Şeyde nasıl kırılıyor? Şeyde. Şeyde o kadar yüksek değil mi?
Onlar şimdi o antrenörü şeyden Automata üzerinde bunun da yani kadar bir şey var. Hayır bahsediyorsun. Burası işte abi. Biraz fazla sorun ama hala hayvanlar bu çok önemli. Tabii konusunu güzel bir ağaç farklı güzel bir şey. Tabii ama mesela bir şey soğuk konuşalım. Okay, so are there any questions? So this composition thing is different from, remember we had a finite state automata. We had a finite state automata. We had a finite state automata for the sheep language, remember? This ba thing, right? And then we said that we like to take the union of, no, we like to concatenate with the bird language, another finite state automata. This is 0 and 1. And we said that we put an NP transition between them. This composition is different from that, okay? This is not concatenation, this is composition. So at the end we are going to take this one and we are going to produce this one, okay? So this is also called cascade, and we are NLP people use this technique a lot because this cascading with the finite state machines is very well defined operation and it can be done automatically. That's why we like it. Okay, our plan is this: come up with these kind of rules and you have your lexicon to finite state transducer. So this is a very nice theoretical word. Okay, in this world, okay, there are no exceptions. In this world there is no irregular verbs, there is no irregular plural singular stuff. Okay, everything is converted with these orthographic rules. In this world, all you do is, if you have this, and if this is a noun, then you do this. If it is a verb, then you put a verb and third person, etc. Okay, so this word is something that we like, but this word is the word that we have to live with. And these orthographic rules, they take care of all those kind of irregularities and produce this intermediate form for us. That's kind of the solution. Okay, so if you have many of these, you would come up with this kind of stuff, with the intersection and the composition and that kind of stuff. This is a composition thing. Okay, if you have a two finite state automata, it is like if you have two functions f and g, okay, fx and g y, this is something like f g y composition. And this is what you do with the composition. If you have two finite state transducers or automata, doesn't matter, create a new set of states that correspond to each pair of states. So if my finite state transducer 1 has n states, and if my finite state transducer 2 has m states, then my new composition, transducer 1 composed transducer 2, will have n times m states. Okay, and for each of these states I will do this transition rules. Okay, transition tools, using some kind of a rule set. There should be a transition between two states in the new machine if there is the case that the output of a transition from state from M1 is the same as the input to the transition. So once output is the same as the one's input, then in that case there should be a transition between two new states, etc. Okay, so this is, maybe you understand this one. This is our new stuff, input and output. If there exists C such that input is converted to a C with the transducer 1 and the output is XP, okay, and in this case YA takes a C and produces an O, okay. In this case for our new finite state transducer, input will be I, output will be O, for this, of course, only for this transition between these two states. Remember, the new states for the new machine will be the pairings of the states of the X and Y states. Okay, this is called composition. And with the it's automatic. We don't do it by hand. It is done automatically. It is done by the finite state automatic tools, and this will be fine. So all we have to do is come up with these kind of orthographic rules. Okay, any questions so far? Okay, let's open our paper. Where did I put my paper? Where is my paper? The paper that I sent you last time? This paper? Let's look at some of the lexical to intermediate form stuff. Okay, this is simple enough. Remember when I say two-level description, when I say two-level description, okay, this is what we mean. Orthographic rules compose with the lexical to intermediate. Okay, so first the paper describes how the rules are defined, and this is a very good introduction about the Turkish the sounds, all the letters, and okay, this is the surface tape to lexical tape. All of these transducer will be put together to come up with one large transducer, and that nicely. Okay, good. Here I have some of the rules. Okay, this H thing is for U, I, E, etc. Then the capital A is for A and A. See, when I say in Turkish kitabı üzümü, okay. So sometimes it becomes sometimes it becomes ü, sometimes it becomes I, okay. It goes like that, right? So this H represents all of them. Okay, sometimes when you say kitaba and I'm trying to find something that ends with an E, like kitaba, because the dative, okay. Kaleme, okay. Sometimes it becomes A and sometimes E. So these are the problems of, not problems, but the rules of Turkish, okay? Like the dropped E rule. We don't make a distinction between A and E in that case, or U or Ü in that case, okay? So in our intermediate form, we are going to say that these two will be represented by an A, capital A. All of these will be represented by, okay, with H. These are the rules, okay? So in our surface form or the intermediate form, okay, ilaç, the zero means is the caret in this case. It's kind of the caret. In our intermediate level, okay, ilaç, there is an L and ior, and lexical one is the L suffix and that ends with a, remember A, what it means, and there is a, so there is a H means, remember, I, O, U, etc. Okay, so these are the orthographic rules. Okay, if you put them together, you will have nice, very nice finite state transducers for nouns. Nouns that will include, what happened? Whoa. Do you guys hear me?
Yes, we can.
Yep.
I lost my second screen. that means that my local copy is, my local recording is messed up. Let me try to fix it. There was a power failure here. Okay, it looks fine. Oh, it looks fine. Okay, good. Okay, so this is a finite state transducer again, to recognize and parse our Turkish words. This is for the nominal nouns, right? Nominals. And I think we have another, this is the continuation of it. And we have another one for the verbs. Okay, so separate finite state transducers, they need to be composed, they need to be unionized together. Okay, so this was done some time ago. People have changed this a little bit, but we are still using it for the main Turkish spell checkers. Okay, so the rules are for Turkish there, and read this one, and there are a few examples. Remember, what did I say? Yeah, this one is very interesting. Çocukları. It has 4 meanings. Yeah, and this is very helpful to understand what their meanings is. Okay, the English versions, when you say çocukları, his, her children, his children, he has more than one child. When you say accusative children, çocukları, okay, çocuklara verin, give me the children kind of stuff. And this is their child, of course, and this is their children. 4 different meanings for this, 4 different morphological parses. Okay, and many. Okay, this is very interesting. This one is too. When I do this çocukları, the çocuk is always the same lemma. Okay, the root has the same meaning. The root has the same dictionary entry, but in this case it is a little bit different. It has 2 different stems. One is al, the other one is alın. This is a noun, right? No. Yeah, but this is a verb, alınmak. Okay, this is a verb too, but this one is the forehead alın. It's a noun. So 1, 2, 3 of them starts from a noun. The rest 1, 2, 3, 4 of them, it starts with a verb. So alınmış is a person, offended person, and alınmış is the past tense of a verb alınmak. Anyway, okay, so read this paper and we will talk about it later. Any questions about this paper or about morphological analysis of Turkish or English? The problem with Turkish is with the inflectional derivational morphology most of the time, there is a dictionary entry. Okay, you can make a verb out of another verb. Okay, compute has a dictionary entry in English. Computer is another dictionary entry. Computerize, okay, is another dictionary entry. So what I am meaning is that these are all different words. Their lemmas are different. Okay, so derivational morphology, most of the time you don't have to deal with it. Okay, I mean, when I translate the sentence, the process of computerization, okay, when I hear that word computerization, I don't have to know that it is derived from compute, then computer, then computerization, right? Because computerization is a word by itself. It has a meaning in dictionary. So that's why in morphological analysis, we don't do derivational analysis much. The important thing is the inflectional morphology. And that's the difficult part for Turkish, because inflectional morphology is difficult in Turkish, but not that difficult for English and similar languages. Okay. Good. Then if there are no questions, let me start the new chapter. New chapter is about language modeling. Okay. We are gonna do language modeling. Previously we did morphological analysis. Now we are gonna do language modeling. What is the difference between morphological modeling and language modeling? With the morphological analysis, we are more powerful. Given a word, we say that it belongs to Turkish or English, and this is our parse. We say that this is the root of the word. These are the affixes. Okay? That's what we say. By the way, let me find that. Where is my paper? Oh, okay. Control C, and here's TR Morph. There was a paper in there. I'm trying to find the TR Morph paper. In that TR Morph paper, I had all the doc. Yeah, okay, good. This is the TR Morph paper. In that paper, it has some list of suffixes. Okay, good. This is a implementation of those rules, two-level implementation, our lexicon and etc. Okay. Where is the list of? It had a list of all the. No, I think I'm mixing it up. All the suffixes, affixes. Oh yeah, okay. So it is just listing them one by one. I thought that I had it as a table. Maybe we had it as a table somewhere. Okay, this is a good paper too. This one implements this two-level hierarchy and it says that this is simple. So let me give you this paper too. Last time I gave you the original paper, and okay. So I send you the paper. Keep this paper. So let's go back to the original discussion. So we did the morphological analysis. With the morphological analysis, we are more powerful. Why do I say that? Because given a word, we say that it belongs to Turkish or not, spelling. Also, we do the morphological analysis of the word, and we say that this is the root, these are the affixes, and etc. With the language modeling, we are not, I mean, given a sentence, we are not going to say, okay, this is a sentence of Turkish or English, okay, especially with this chapter. We like to say that, but we won't produce parse trees yet. It is not that easy. What we are gonna do is we will do, especially at the beginning, statistical language modeling. Statistical language modeling. What do I mean by statistical language modeling? If somebody gives me a sentence, I go to school very early. Okay. What is the probability of having such a sentence in English? We are trying to answer this one. We are not going to say yes or no, but we are going to say, what is the probability of having such a sentence in English? Okay. Difficult to estimate this probability, but if we have a very large English sentence database, we call that a corpora. Okay, very large English sentence database. Looking at that English sentence database, I will try to see if this kind of a sentence is possible with that database. Okay, so this probability will never be zero. Okay, there is always a chance that such a sentence can happen, and this probability will not tell me that this sentence does not belong to Turkish or English. It will only give me a probability. Previously with the morphological analysis, we didn't do that. We say that accept or reject. If it is accept, then this is our analysis. In this case, with this language modeling, especially with the statistical language modeling, we will not do those kind of parses yet. Parsing will come later. So we are trying to do something a little bit less than morphological analysis, full-scale analysis of the sentences. We are trying to model the whole language, the Turkish or English, in this sense. By the way, if you can calculate this one, maybe you can do this too. Let me do it this way. Arc max W and let me erase this part and put W here. Find me a W in English. Okay, find me a W in English that makes the probability of this sentence possible. Okay, that makes the probability of this sentence is possible. How would you find such a word W? I will take all the words in dictionary, right? I will take all the words in dictionary. I put them in here and I calculate this P and pick the one that makes this P maximum. Okay, that makes this P maximum. So this is a very powerful way. So if you model your language statistically, that means that you may write your own sentences by following this rule. What makes it possible? What makes it the highly likely? This sentence or that sentence, and we will see. So when I say we are not going to do full-scale analysis, I am not saying that we are going to do something useless. It will be very, very useful. Okay, it will be very, very useful. So word prediction task, the task that I just showed you, what makes the probability of this sentence maximum? To do that, I will introduce some new concepts, engrams, very simple concept, but very powerful. Then chain rule, you already know this rule from your mathematics courses or the probability courses. And then we will talk about, okay, with this nice modeling, but how do we know that it works? Okay, how do we know that it works? How did they know that this one works? And how did they know that? How did they know that this two-level morphological analysis work? Well, they tested almost all the words, and it looks like it is handling all of them, right? We will not be that lucky with the statistical language modeling because it will never tell us that okay or not okay. Okay or not okay, because it will give us probabilities. How do you test the probabilities? That's called model evaluation. How do you know that the things that we did is correct? That's a very difficult job, actually. I mean, how do you evaluate your way of calculating those p-values? And smoothing is something related to that one. Okay, so let's look at this example. Here is a sentence. I noticed 3 guys standing on the question. What would you put in this position? Question for you. What would you put at this position? Just everybody type a word. Type a word on your chat window. I noticed 3 guys standing on the deck, wall, standing on the wall. Gökçe, that's interesting. Sofa. Oh, so Yusuf, that's interesting too. Stage is good. Road is good. That's very nice. Okay. 1, 2, 3, 4. Ground. Ground is good, Aynur. That's it. Only 5 bench. Okay, sure. Legos. Doğancan, what kind of world are you living in? Lego. You are okay. Good. So nobody repeated the same thing, but nobody said. I noticed 3 guys standing on the like. Nobody said this. Carpet is good. Okay. Nobody said this. So you are picking a noun, right? You are picking a noun. But for example, like is not a noun, it's an adjective or verb maybe. But nobody picked a noun like soul, ruh, right? So because nobody can stand on the soul, right? So you are picking correct form of the word. You are picking standable things, right? Like carpets or shores or bench or if the Legos are large enough and the guys are small enough, then Legos are possible too. So what do you need to know to complete the sentence? What do you need to know about natural language processing and the real world? Okay, of course you need to know the grammar. Grammar will tell you that standing on the like is not, it is not possible. It's the grammar. Also, you need to know the real world, the world that we are living in. You cannot stand on abstract things. You need to stand on large enough physical stuff, right? Large enough physical stuff. So it's a difficult problem then. How would you find such a thing? You need to know morphological analysis. You need to know the syntax of the language. You need to know about the common sense knowledge, real world knowledge. What is standable, not is not standable. What would take my weight, what would not take my weight. I don't think that you're gonna say I noticed 3 guys standing on the a glass of water. Okay, no, it won't. It will not work. Okay, so it's a difficult problem, but it looks like we can do very good by keeping statistics of the sentences or the words that we have seen so far. We can come up with very good examples. Okay, so maybe I can just let me. Can I do this? Can I? Wow. I am trying to copy it. How would I do this? Select maybe? Select? Yeah, do this. Okay, good. How come it doesn't work? Okay. I am trying to copy this and copy it and paste it to my favorite. Okay. When I do this, usually when I put a space, Google tells me that this is more likely. Okay, let me make this. Okay. I noticed 3 guys. Sheet music is the most possible one because I think people are making lots of search on it. So the point I am trying to make is Google has seen many sentences written by human beings, and many people had written, I noticed three guys, sheet music PDF. Okay, so it looks like maybe it is not related to I notice, maybe it is just three guys, right? Three guys. No, it is pizza. Come. Okay, maybe notice three guys. Notice three guys. Doesn't give me anything. Oh, okay. I noticed three. What's going on? Okay. When you say
have to enter the Google first.
what's that?
If you enter the Google, they give you subjection.
If I enter this, it will give me. You mean type it in here? When I say I notice three so when I say three guys, it gives me some stuff. Three guys. If I do this, what would I get? It doesn't give me anything, so I need to put this I at the beginning. The point I am trying to make here is that Google has seen many people typing sentences. It says that looking at all those statistics, I am thinking that this is the most possible word because people have been typing it that way. So statistics is important. Does Google know the real world knowledge? Does Google know the Google search engine about the language? Well, in that case, it doesn't use that kind of knowledge. All it does is keeping statistics. Okay, what kind of words do I have before me? What kind of words have I seen? And what makes this sentence more probable? Okay, what makes this sentence more probable? Okay, so this is the sentence that we are going to deal with a lot. It turns out that we can do very good by simply looking at the preceding words and keeping track of some fairly simple statistics or counts. Okay, how many times did I see standing on the, and how many signs, how many out of that many, how many of them are, for example, shore, Legos, or carpet, or road? Okay, so we will have this kind of statistics. In fact, Google makes this available for you. Google Engrams. Okay, this Google Engram viewer says that. Okay, three guys standing. So I am asking Google, how many times did you see three guys standing between 1800s and 2019? These are the probabilities. Okay, so in 2013 there is this three guys standing. For some reason it made a peak. I think it is a title of a movie or something like that. Okay, so these are the probabilities. So how does the Google know about this? Because it keeps the statistics. So I'm going to do this then. I'm going to do this. Let's see which one of your answers is the best answer. Carpet and three guys standing on carpet and on, let's see, some Legos. Okay, let's see what's happening. Well, it says that I cannot find these. Oh, okay, I didn't. Sorry. Okay, do it again. it says that no, I cannot find any. Google did not see anybody typing 3 guys standing on carpet or 3 guys standing on Legos. Maybe the carpet and the Legos. Again, no, unfortunately not. And do you think that Google did not see some of these sentences that have been written in English? That may include, I noticed 3 guys standing on the carpet, or 3 guys standing on the Legos. Well, Google says that they formed this interface, Google Books Engram Viewer, by scanning all the English word, all the English books available in the world, starting from 1800s. This is very powerful tool. Okay, if Google did not see such a sentence or such a sentence phrase, then nobody has used it before. But does it make it grammatically wrong? Does it make it semantically wrong? No, it is a perfectly valid. I noticed 3 guys standing on the carpet. I mean, I can use this. I cannot believe that I am the first one to use such a sentence phrase, right? But it looks like Google said that at least nobody has written it on a book. Otherwise, Google have picked it up. Okay. What does this say us? I mean, what does this tell us? Does it tell us that there is no hope that we can use statistics to come up with this probability? Okay, because it looks like even the simplest sentences was not used by anybody else. The answer is no. We are going to use probabilities, and we will be doing it in a smart way. We won't be doing it in a straightforward probability case. Okay. Standing on the carpet is there, but notice standing on the carpet is not there. Well, maybe we should be more fair. Google does not keep statistics of sentences that did not occur less than 40 times. Okay, if it has occurred less than 40 times, Google says that I am not going to give you the statistics. That's not statistically significant enough. So probably it has seen a few of them, but not many of them. Okay, but the problem is there. I mean, if you like to model your language using this modeling tool, the statistical modeling tool, there will be perfectly valid syntactically and semantically sentences that you have never seen before. Okay, so if you are looking for those kind of sentences, that did this sentence happen before, and if the answer is no, that doesn't mean that that's a bad sentence. It might be a low probability sentence, but that's not a bad sentence. Okay, so play with this Google Engram tool. Okay, let's maybe do it less complicated. Standing on the carpet, like Doğancan suggested, and standing on the Legos. Let's do this, and the answer comes back. Standing on the carpet is a lot. Standing on the Legos, no, Lego is okay. No. On the Legos, how many times on the Legos? Even on the Legos is not there. Yeah, on the Lego is there, but standing on the Lego is not there. On the Lego is very small. By the way, we use this to, okay, see this one? Lego is something that was popular for some reason 18 something, but in 1940s, 30s. I think that company was founded in there, right? So this peak is there. I don't know what this peak is in the vitiligo. If you look at the word, you're gonna see it. So this is interesting. This is So even before 19, what is the time for our the name law, last name law? I think 1930s, somewhere there, right? So even before that, for some reason there is a probability, but the peaks are happening around 59 and 95 and 2014. Okay, so there are some peaks in there. So this is interesting what people are talking about. Oh, because İnönü has a different meaning because that's the name of the town, right? By the way, these are the probabilities. These are not the occurrences. Probabilities of that thing happened in that year. Okay. So, okay. I know what the problem is. It is case sensitive. Yeah. So most of the time it is spelled this way. Anyway, so you play with this, and 1934 is the year. 34 is here. Okay. There is a peak in, I think in 1940, his death, Atatürk's death, lots of news about it. In 1960s. And people are starting from 2000s, they started using this proper name, Ü, not U, but Ü. Maybe we started having keyboards that can type Ü, the letter Ü. Anyway, so play with this. This is fun. Play with this. It's fun, yeah. Case insensitive. This is case insensitive. Yeah, okay. How come I am not getting this then? Yeah, but case sensitive doesn't care about our Turkish conversions. Anyway, okay. Let me go back. Okay, so we are gonna do this. We are gonna use statistics to calculate the probabilities of the sentences. But calculating the probabilities of the sentences doesn't mean that did I see this sentence before, okay? We are gonna do more than that. We are gonna be a little bit more smarter. By smart, I don't mean that we are gonna do lots of mathematics, but we will do some mathematics. And in fact, most of the time, we will be doing this small engrams, 1 or 2 grams, okay? Let me give you the definition of an engram, and we will stop for 10 minutes. The engram is token sequences of length n, okay? These are some 2 grams. I notice is a 2 gram, okay, or bigram. We sometimes go to bigram. Notice 3 is a bigram. 3 guys are bigram. So if I go there, there is one bigram, 2 bigrams, 3, 4, 5, 6. There are 6 bigrams in this sentence. Okay. So this is what we call an engram. Instead of trying to see how many times I have seen this sentence, I noticed 3 guys standing in our Google database, we will try to do some kind of a combination of how many times did I see I notice, how many times did I see notice 3, how many times did I see this engram, this one, and this one, this one, this one. And then we are trying to make a guess how many times did I see one after the other one? Okay, that will be the idea. That will be the idea. Okay, so let's take 10 minutes of break. Let's be here around 15:35. Okay, so break 10 minutes.
Maskeler şey oldu. Maskeler maskesi. Yani anlamadım. Yani maskeler şey ya. Devletimiz bunu veriyor. Ha? Devletimiz bunu veriyor. Nasıl? Yani devlet kullanmıyormuş o zaman kendim için kullanıyorum. Kim hatıramız verdi? Ama şu ne? Demek ki kimyasal ışık ultraviyole kimyasal etkileriyle ölçüyor. Yani üstünü kaplasaydık gitmeyecekti yani. Kaplasamak gitmeyecek. Evet. Gitmiştir ama şu anda insan falan da hocam şurasında değişikliği yok ama mı? zaman hiç aynı şekilde ilerliyor. Ve beraber yükseliyoruz. Aradaki farkın azalması aslında yükselmemizle alakalı. Yoksa azalmıyor yani. Yüzdelik baksan 3 aşağı 5 yukarı aynı yerde olabilir.
Çünkü yani bunun şurada yükseldiğini, şu kadar şurada yükseldiğini, bu yükselmiş. Tamam mı?
Böyle bir bakmak, bir çıktıkça şeyler azalacak.
Evet. Ama bizimkisi şeye gitti mi? Döner mi? Şurası döner mi? Şurası döner mi? Yani şurada biraz eksponansiyelde şurada. Şurada yukarı. Şimdi döner mi? Seriye. Ama şuradan itibaren, nereden itibaren? Bak şuradan itibaren herkes haklı. Şurada. Şunlar şeyden düşer.
Hala biliyorum.
Adam buraya kavuştu ya. Kendi aralarında. Şunları da gör yani bu. Şeyden, Eskişehir'den, Kocaeli falan ayrılıyor. Karıştırıldığı için. Yani şuraların altına geliyor. Şunlarla beraber gelir. Biz de hocam bu arada kalalım ya. Biz şu anda bir dakika bu yenisi yok. Bunun yenisinde biz şuraya yaklaştık bak. Evet. Şu Marmara mı? Marmara. Yani seneye şunun ikisinden bir tanesinin dibine düşmemiz lazım. Neyse hocam ben bitersin. Okay, people. So we are going to use statistics to model the language, and that's going to be very, very useful for a number of tasks. Our modeling will not be as powerful as the morphological analysis, but it will be very useful for a number of cases. Let me take today's attendance. Just a minute. Okay. I got the attendance. Okay. As I said, instead of looking for whole sentences, we are going to look for smaller parts of them, and we are going to put them together in a meaningful, mathematically justified way. We are going to use engrams to assess the conditional probability of a candidate word. What is a conditional probability? Okay, the conditional probability is this. Let's say I have three words. What is the probability of having these three words together, standing on the, okay? A is, okay. This is the okay. A is standing, B is on, and C is the. What is the probability of having standing on there? Okay. And we know the conditional probability. The conditional probability of this is, okay, given, let me make it a little bit easier for us, a little bit more, okay. Let's keep it simple. Standing on. What is the probability of standing on? Seen in an English text, standing, giving this two words together, standing on. It is, what is the definition of conditional probability? It says that PB on times P given B on and the probability of A standing. Sorry. Okay. That's the definition of conditional probability, right? That's the definition of conditional probability. And we can just do it in a way that we can isolate this thing. Okay. You could say that I am not going to type this standing and stuff. P A given B. Okay. It is P A B and P B, right? We can write this too. So we are gonna use just this definition. By the way, there is no proof for this. This is just a definition of the conditional probabilities. We are gonna use this conditional probability mechanism to calculate the probabilities of complete sentences, but we are gonna do it in a conditional way. What do I mean by conditional way? We'll say that I have seen the words on. Okay, what is the probability of after on standing? Or I have seen the word standing. What is the probability of on, etc. After that? Okay, and if we model our language in this way, statistically, it will be useful in many cases, like the automatic speech recognition, character recognition, spelling correction, machine translation, and many more. I already told you those. Okay. So the problem that I mentioned before, trying to find the statistics of whole sentences is difficult. Okay. So this is a very nice sentence. I think it is taken from a story or from a novel. He stepped out into the hall, was delighted to encounter a water brother. Okay. So this one has 13 tokens. And if you count comma and period as a token, it is 15. Okay. So if you like to count the bigrams there, what are you going to do? You're going to do just this. This is 1, and then stepped out 2, and out into. And if you are counting these 2, okay, there will be how many? Okay, if we have 15 tokens, how many bigrams do we have in this sentence? If we have 15 tokens, eight, but you are missing this. You are missing this one, right? So he stepped is a 2 gram, right? He stepped is a 2 gram, but stepped out is another 2 gram. You got it? Okay. So how many? If we have 15 tokens, then we have 14 bigrams, right? Is that correct? 14? because every word has to be in a bigram, and other than the first and the last words, everybody will be included in 2 bigrams. Okay, so there will be 14 bigrams in that case. Well, that, of course, there are many problems with this. For example, this is for written English or Turkish only. If you are talking about spoken language, like when I talk about Turkish or in English, I keep saying or I keep repeating the same word over and over again. As you see, I repeat the same phrases over and over again. It is not easy to make these calculations, but it looks like we are going to deal with the nicely written sentences. I will not deal with this kind of spoken English or Turkish stuff. Okay, counting is not that easy, but we are gonna ignore the details for now. Some of the details we will try to see, and some of them we won't. Okay, so counting has its own problems. For example, when you count cats, are they the same word? I mean, how many cats do I have in this sentence? How many cats do I have in this sentence? Is cats and the cat the same word, or they are different? Okay, I have cats and I have cat. Are they the same sentence? No, of course not. But for the sake of counting and keeping statistics, can I consider them as the same words? Again, we are not going to deal with this kind of details. It is not because they are not important. They are important, but for the sake of keeping things simple, we will ignore these kind of problems for now. Okay. So remember I talked about Corpora, the database of English text or the Turkish text. I have 2 examples for you. The first one is Brown Corpora, 1992. During those days, we didn't have internet. It was not as popular as today's internet in 1992. By the way, I think this is a 1992 paper. How old is this? I think this is beginning of 1990s. Look at the address. See, we didn't have internet during days, okay? But the email mechanism was there. This is Bitnet. Before internet there was Bitnet, and we used to use Bitnet. With the Bitnet, if you are lucky, sending and receiving an email would take a day, whole day. Okay, so in 1992, so I'm telling you that in 1992, having such a large corpus was very good. Okay, so they said that they have more than 500,000 tokens in their Brown Corpora, and they have total of about 300,000 word form types. Then, beginning of 2000s, Google said that I have scanned all the English books, everything. I have scanned everything. Okay, and it looks like I have this many tokens. How many tokens are there? 6, 9, 12. Is this 1 trillion? Is that correct? That would be a billion, right? This is 1 trillion tokens, and there are a total of 13 million word form types. Why so many word forms? I mean, what's a word form? Word form is a each word. I mean, it's like a this is a word form. Okay, this is a word form, something like that. Okay, let's do the English. Okay, this is a word form, and this is a word form, and maybe this is a word form. So there are 13 million or almost 14 million word form types. Why there are so many compared to this one? Well, in English dictionary, there are 400,000 types in an English dictionary, even the largest one, such as the Oxford English Dictionary. Okay. Has anybody seen this movie, The Professor and the Madman? The Professor and the Madman. Doğan Can said he did. Okay. If you did not see it, it's a very good movie. It is related to how this British people see their language. Okay. They started working on their English dictionary end of 1800s, and it took them 70 years to complete the whole dictionary. At the end, they had 400,000 words defined. Of course, with the dictionary, they need to find the roots of the word. By roots, I don't mean the stem. Okay, it is where does the word come from, who used it, and how frequently they used it. And they are doing this at the end of 1800s. They don't have any computers. Okay, so let's say they talk about this word approve. The word approve, who used it first and when they used it, do we have any quotations and etc. So without a computer, finding all of this stuff will take time. So it talks about what kind of work goes into forming a dictionary. And it's no surprise that it took more than 70 years to complete that dictionary. Even that dictionary has 400,000 words in it. 400,000 words in it. So how does the Google find 13 million words? Because for Google, even the numbers, misspellings, names, acronyms, and etc., they are like words. So Gebze is a word in a dictionary. I don't think that you're gonna see Gebze in Oxford English Dictionary, right? That's what I'm saying. Or the abbreviation like the USA or USA or the FBI, etc. Okay, so the proper names, the names of the cities, name of the people, acronyms and etc. They all make words. That's why they have so many. Okay, so I told you two corpora in this case. Okay, so let's go back to the word prediction game. How do we predict the game? This is what we're gonna do. I have seen given W, W1, W2, Wn. What is the probability of this Wn? Conditional probability. If I could calculate this conditional probability, then I will be fine. Why? Because I know that if I could calculate this one, right? If I could calculate this one, by multiplying this one with this, I would calculate this one. That was the definition of conditional probability. You'll be fine if you can calculate this one or this one. Okay? Both of them will be fine. So this is more attractive for us because I have seen the first n-1 words of a sentence. Given those, what is the probability of having this word at the end? Okay? Remember when I said I noticed three guys standing on, then I need to find a word. I need to find a word after that. And this probability, if I can calculate it, it will give me this one. And if you can do this, you are modeling your language using statistics. Okay? How do you model your weather prediction? Okay? How do you model your weather prediction? How do you know the probability of having a rain today, or cloudy weather today, or snow today? Okay? That's called weather modeling. And weather modeling could be done using different techniques. One of them is the statistics. Okay, one of them is the statistics. You keep statistics of how many times it rained in Gebze for the last 50 years on this day of the year, October 26th. Okay, so use that information to find an answer. So it's the statistical model of the weather. The statistical modeling of the language is how many times did I see such sentences, etc. That's what we are trying to do. Okay, so if I like to calculate the probability of having a "the" after this sentence, subsentence, its photos is so transparent that what is the probability of having a "the" after this 1, 2, 3, 4, 5, 6 words? Okay, so write the same thing again, over and over and again. P A B is P A and B occurring together over PB. If this is the formula, this is the definition of the conditional probability, then this one equals to this one. It says that go to your corpora, the Google corpora, okay, count the number of times that you have seen its water is so transparent that, okay, so this will be your, this is your A, this is your B, and this is your A. Okay, given B, probability of A is equal to PAB over PB. Okay, so count how many times its water is so transparent that, and count how many times its water is so transparent that the, okay, and divide them. That's what the formula says. Okay, if you find the counts of these or the probabilities of these, then you should be fine. So that's the formula. Again, this part is A and this part is B. It is that, okay, count of A over count of AB over count of B. How many times did you see this? And after each of them, how many times did you add an "the" in it? Okay, the thing is that if you make a search on Google, okay, in Google it says that I have seen this sentence 9 times. Okay, I have seen this sentence 9 times, and on 5 of them there is a "the" at the end. The problem is that this is a too little statistics, and many of these sentences from Google comes from these slides, these very slides. Okay, so that's not a good statistics. That's not what we're going to do. We are not going to count the whole sentence. Okay, so we are going to do something else. We are going to do some probabilistic approximations, and we are going to do some mathematics. Okay, so and we are lucky that we have seen this sentence before. Most of the time you won't be able to see the sentences. Where is this? Let me go back to, if I do this, I noticed 3 guys standing on the, okay, if I make a search on it, well, it says that I have found 7 results out of all the Google stuff, and as you see, they all come from, this one comes from the slides, right? This one is a NLP course. This one comes from the, again, this one is come from the NLP people, again, sidewalk sidewalk, it looks like, so this is different. On the side of the road. So the number of times I have seen this is just 7, which is a very small statistics. And I was lucky that I have seen it, because most of the time I will get 0 standing on the carpet. Yeah, it says that it is just 0. Well, it's a perfectly valid sentence, but it has just happened 0 times on the whole internet and the scanned documents of the whole Google corpora. So we don't want to do this 0 over 0 thing. I never seen it. So we are going to use the chain rule to make an approximation to this probability calculation, and we are gonna say that, okay, even though these two are not equal to each other, this approximation is going to work for us, because all we need to do is maximize this probability. We are not trying to perfectly calculate the probability. We are trying to maximize it. Okay? We are trying to maximize it. This is the formula that I gave you before. Again, this is the definition of conditional probability. Conditional probability, I'm sure you have seen it, is a very powerful modeling technique. It is used for many cases, especially for the diagnostics. When you like to diagnose some stuff, for example, doktor için teşhis koyma, what is the probability of disease being cancer if the patient temperature is 37.1 and the patient is coughing? Okay, coughing is true. And what kind of other? Okay, the pulse rate is 60, and let's not use this. Okay, pulse rate is 60. Blood pressure, high blood pressure is 16.7, etc. Okay, so given all this data, what is the probability of patient having a flu? Okay, so the doctors use these kind of reasoning techniques. So how do they calculate this again? They say that all of the patients that I had seen before, what is the probability of disease being flu? Okay, and temperature is such and such, coughing is that, pulse is that, blood pressure is this, over P without this disease, TCP, blood pressure. Okay, so doctor says that I have seen this many times. When the patients come with this kind of stuff, this many times I have seen that they had the flu. So I'm gonna say that this is the probability of this patient having the flu. The doctor never says that you have definitely flu. He says that 90% you have flu. Okay, this is conditional probability. It is powerful. It is used everywhere. What is the probability of email being spam, given that in my email the first word is money, the second word is easy, the third word is rich, etc. What is the probability of having this email spam label? Then it is so that means that you're going to scan all of your emails before, and how many of them are, in this case, how many of them are marked with a spam and how many of them are not marked with a spam, and you do your calculation. Again, the conditional probability thing. Okay, conditional probability thing. That's, Selman, you are saying that there's 100% spam? No, I don't think so. It is not. It may not be spam. It may not be spam because it might be talking about, this email might be talking about spam emails. Okay, so it might say that it might be coming from our IT department, Bilgi İşlem Merkezi. Okay, and it might say that if you have seen emails that contains these words, then it's probably a spam. So it's not a spam. So I wouldn't say it is 100%. So this is conditional probability, and the formula for conditional probability is this. And if you replace this B with B, C, D, okay, then it becomes B, C, D and B, C, D. So B doesn't have to be a single random variable. It could be more than one. Okay, it could be more than one. So that means that when I say P, A, B, C, D, okay, let me do it with just 3 of them. P given B, C, okay, times P B, C. I can write it that way, but this BC is same as this one, right? BC is same as this one, so I can expand this part with this one, and it becomes something like this. This is called the chain rule. Chain rule. Probability of having A, B, C, D, these words, is PA times P given A probability of B, given AB probability of C, given ABC probability of D. And in general, I can write it this way. Probability of having these words together, N words, is these. Okay. So it looks like I don't have to calculate the probability of having a very long sentence of N words can be separated into these probability calculations. This one is easy to calculate. How many times did you see the word X1? This one is easy to calculate. All you need to do is how many times did you see this word and how many times did you see both of them together. It is not as easy as this one, but it is again easy. This one is a little bit tougher, but when I come to this one, this is, although it is a little bit simpler than the original problem, but it is still not that easy. This one is not that easy, right? So we made some progress. Instead of calculating this whole thing, which is not easy to calculate because we don't have enough statistics, I separated this into n smaller factors or the parts. At the beginning, this is easy, kind of easy, but this one at the end, it becomes more and more difficult. It is as difficult as the original problem. So I made a good progress, solved some of the problems, but this one remains there. So for this one, I cannot continue. I will have to do some approximation. Can anybody guess what kind of approximation I am going to do? Especially for this kind of part.
P1 union P2 equals P1 times P2 maybe. Like that.
Just say it again. P1 P1
union P2.
What do you mean?
Yeah.
What do you mean? You mean plus?
I mean, you generally put a comma in your notation.
How? What? Just a minute. Just a minute. I cannot erase this. I cannot erase this. I
It's
cannot.
the event space.
You mean times P2?
No, P1 is the event space, and
P1?
P2, and the probability of them.
Together, then you mean P1 times P2.
Mm-hmm.
And then, yeah, it is equal to?
P1 and P2 being happening at the same time, being joined.
Well, you just give me the definition of. You just gave me the definition of P, A, and B. That's what you did, right?
No. If they are, if they have, how can I say, common events, that's not direct to the.
Well, I mean, they are all related to each other. They are not independent. They are all dependent to each other.
Yeah. But
So you are saying that if P1 and P2 are not related, then I could do this, right?
Yeah, we can just assume they're disjoint.
I cannot, because as you see, X1 is common between them. They are not independent.
Yeah, but
So you are saying that
it's just a bit.
what is the probability of a patient having a flu? Right? That's what you are saying. What is the probability of a patient having a flu? And let's say what is unrelated to a patient having a flu? It is not the day of the the day of the week is Friday. Patients, they have equal chance of getting flus on Friday or Saturday, so it is the same as probability of patient have a flu times today being Friday. So you just multiply both of them. But these two are not related. I mean, patients can have flu on any day of the week. On Mondays, you don't have more flu patients. But in this case, X1 is common between them. So it says that what was our original sentence? Original sentence is, its water is so transparent that, so it says, what is the probability of given its water, right? What is the probability of given its water? So, okay. So they are all related. I cannot make this assumption.
Okay, I just thought, since we are approximating.
That would be that's an idea, good, yeah, but that wouldn't take us very far away, very. That wouldn't take us towards our final destination. Anybody else? How about this one? Do you think probability of its water, let me write it a little bit. Okay. For some reason, even though my pen works this one, let me start my application again. This time it's not pen problem, it is the application acting weirdly. So what I'm going to ask you is something like, do I have to go way like 10 words before my current word is it enough to I did a bad thing, but that's okay. That's okay. Where was I? So here was I. So probability of it's okay. We said that its water is so transparent. How about this one? Can I say its water is so, given its water is so, how about this one? Probability of water is. How would you compare these two probabilities? What is the probability of having so after water is compared to probability of having so after its water is? Some people say that these probabilities are very similar because looking at just two words before the current word should be good enough to understand the context of the word so. Okay, so why do we have to go to 3 words or 4 words before the current word? Okay, let's assume that these two are kind of equal, and if these two are kind of equal, then I don't have to calculate this one. Instead of calculating this one, I would calculate given xn2 and xn minus 1. Okay, so that means that I will only calculate trigrams, like 3 grams for these 2 grams, for this 1 gram. Okay, so this is very convenient. Instead of calculating this whole very large thing, which is not possible to calculate, I don't have enough statistics, I would just calculate a 2 gram version. Okay, so that's an approximation. So to calculate the probability of this sentence, its water is so transparent, the chain rule says that calculate the probability of x, then multiply with this one, then this one, and this one, and this one. But I say that, okay, it is easy to calculate this one and this one, but it gets difficult, and this one is going to be very difficult because this one has 1, 2, 3, 4, 5 gram, and calculating 5 grams is not that easy. By the way, how many 5 grams are there in Google's corpora? Maybe this is just 1 gram, right? How many 1 grams are there in Google's corpora? Question for you. How many 1 grams are there in Google's? Let's go to Google's corpora again. Yeah. How many 1 grams are there in Google's corpora? Anybody? It looks like I lost many of them, huh? Okay. Then I will pick one people in random. Okay, so at the beginning I have more than 40 people, and I have 39 people. Okay, this is kind of a attendance check, maybe. Okay, Don't go to Y's. Let's pick them from the beginning then, this time. Okay. Aras Topuz. Aras, tell me how many unigrams or 1 grams there are in the Google corpora.
I don't remember, sorry.
What?
I don't remember, sorry.
I am not asking you to remember it. I am showing you the slide. Can you see the slide?
Yeah, I'm seeing the slide.
So I'm giving you all the numbers. I don't ask you to remember something.
Sorry. The English tokens or word form types?
How many unigrams do we have in Google's corpora? What is a unigram, Aras? What is a unigram? Aras, what is the unigram? You are saying something, we don't hear you.
Is it word? No.
Yeah, it's the number of words, kind of, right? It is number of words. So there are 13 million word form times, and that means that there are 13 million unigrams. How about bigrams? How many bigrams are there in Google's corpora? How many bigrams, or 2 grams? What's a 2 gram? This is a 2 gram, right? 2 gram. So what is a 2 gram? Okay. What happens is another 2 gram. Happens when is another 2 gram. So how many 2 grams do you think there could be in Google's corpora? So if I have 13 million words,
The half of them, maybe?
you multiply them, yes. You multiply 13 million by 13 million. Okay. So that's how many okay, that's how many potential bigrams you have in Google's corpora. Okay, but if you have 5 grams, that means that 13 times 10 to the power 6 over 5. That's a very, very big numbers. Okay, that's a very, very big number. It's like 10 to the power 30. Okay, so that's not going to be very easy to calculate. So calculating 5 grams is so difficult, even for Google. You don't have enough data. Even if you have enough data, you will not have enough space to put all the 5 grams somewhere. Okay, so to calculate this one, you need to calculate the 5 grams, and calculating 5 grams is not easy. So what are we gonna do? We are gonna say that, okay, I can calculate this one, and this one, but instead of calculating this one, I will calculate P. So water was, and then instead of calculating this one, I will calculate transparent given was so. Okay, so at most I am calculating trigrams, and calculating trigrams is much easier than calculating 5 grams. Okay, so that's what we are gonna approximate our chain rule. We will say that okay, our conditional probability is almost same as this one. instead of counting all the words from the beginning, count the last N of them, capital N of them. Okay, that will be our approximation. But it looks like I am out of time for today. Next week we will start from this position. Please, before coming to class, read what or listen to whatever we have learned today, because we will continue from where we left off. Quant, yes, that's true. Word form is each word form is 1 gram, and 2 gram is a combination of each word form with another one. That's why the number of 2 grams is the square of the word form, total word forms. So the Google's corpora has 13 million word forms. 30 million times 30 million is the potential number of 2 grams. Most of them will be empty, because many words will not come together at all. Okay, so most of the 2 grams will be empty, but you have to calculate them anyway. Okay, are there any questions? If there are no questions, then we will continue next week. Okay, see you next week then.